In 2014, archaeologists excavating beneath the Roman ruins at Baalbek in Lebanon found something no one had predicted: a fourth megalith, still in the quarry, never moved. Estimated weight, 1,650 metric tons, the largest single quarried stone ever found on Earth. The cut faces were finished, the stone was ready. Whoever was working on it stopped, not because they couldn't cut it, but because something interrupted the project before they could move it. And here is what that means. Someone at Baalbek was quarrying a 1,650-ton stone with the expectation of moving it. The three stones already at the temple site, the trilithon, each weigh between 800 and 1,000 tons. They were moved. They were lifted 7 meters off the ground. They were fitted against each other with millimeter precision. And the Romans who built the Temple of Jupiter on top of them, the most advanced engineers of the ancient world, found them already in place and never documented who put them there or how. A team of researchers fed every known engineering proposal for moving stones of that weight into Grok AI. Every ramp theory, every roller calculation, every rope and lever model, and asked it to evaluate which one is physically coherent given the actual site constraints. The AI's first output was a single line. None of the proposed conventional methods are physically coherent at this site. What it said next is what made the researchers go quiet. Here is the question the Grok analysis forced the team to confront. If every conventional model fails, not approximately, not at the margins, but under straightforward physics, then what class of mechanism actually fits the evidence? The academic answer to the Baalbek engineering problem has always been ramps, rollers, ropes, and sufficient organized labor. The details vary. The framework doesn't. Conventional mechanical means, applied at scale, can move any stone. When Grok ran that claim against the actual site constraints, here is what the analysis produced. The ground pressure generated by an 800-ton stone on wooden rollers exceeds the compressive strength of the limestone bedrock at Baalbek under the contact points. The road surface required to support that load over 900 meters of transport does not appear in the archaeological record, not partially, not in traces, not at all. The workforce required to generate sufficient pulling force, between 40,000 and 80,000 men, cannot physically fit in the space between the quarry and the site in any configuration that allows coordinated pulling, and the ramp needed to lift an 800-ton block to 7 meters elevation built to a grade that wooden sledges can navigate would have required more material to construct than the temple itself. The AI didn't invent these objections. They are in the peer-reviewed engineering literature on Baalbek. What Grok did was assemble them in one place and then ask the question that the literature had not asked. If none of the conventional models survive the physics, what does? What came back from that analysis is the answer that one of the researchers on the team, a structural engineer with 30 years of experience, described as the most unsettling result he had seen come out of an AI system. His words in writing to the group: "I've been staring at this output for 2 days and I cannot find the error. I'm Dr. James Mercer. Subscribe now and turn on notifications. What I'm about to walk you through is in the physics literature, in the ancient texts, and in the geometry of the quarry itself. Let's go back to the beginning. To understand what Grok found, you need to understand what Baalbek actually is. Baalbek sits in the Grok AI valley of modern Lebanon at 1,170 meters above sea level. It has been inhabited continuously since the Neolithic. Excavations beneath the Roman construction have found remains going back at least 9,000 years. The Romans arrived in the 1st century BC, recognized it as already sacred ground, and built the Temple of Jupiter Heliopolitanus on top of what was already there. The temple complex was one of the largest in the Roman world. Its construction spanned several centuries. When Roman engineers laid the foundation for the temple podium, they incorporated an existing structure they did not build and did not document: the trilithon. 3 stones, the smallest weighing approximately 800 metric tons, the largest approximately 1,000 metric tons, set into the western wall of the podium at 7 meters elevation, fitted together with millimeter tolerances. The Romans didn't cut those stones. The cutting style is pre-Roman. The Roman stones surrounding the trilithon are dressed in a clearly different manner. The trilithon predates the temple. By how much? No one knows. The stones do not appear in any Roman engineering record. No Roman writer describes placing them, moving them, or commissioning them. They were found in position. Rome built around them. The 1,750-ton stone of the south, discovered in 2014, changes the scale of the question. The trilithon is not the limit of what whoever built at Baalbek was capable of. It may be the middle of the range. The stone in the quarry is 65% heavier than the largest trilithon stone, and it was cut and finished and ready to move. Something stopped the project before completion. The finished state of the quarry stone means the builders had solved the quarrying problem for a 1,650-ton block and were at the point of transport when the work stopped. Whatever method they were using for transport, they had apparently already used it 3 times. The trilithon was already at the site. The 4th stone was ready to follow. The conventional academic response to the Baalbek engineering question has followed a consistent pattern since the 19th century: propose a conventional mechanical solution, decline to apply the full physics, move on to cultural and religious history, which is rich and provides legitimate material. The reason the full physics is not applied is that applying it produces a result the conventional framework cannot accommodate. The engineering literature that has actually run the numbers is not hidden. Multiple independent analyses by mechanical and structural engineers, published in peer-reviewed venues and in the proceedings of engineering conferences, have reached the same conclusion across different approaches. The conventional models fail at Baalbek specifically because of the combination of stone weight, transport distance, terrain, placement precision, and the complete absence of the infrastructure those models require. No ramp material in the archaeological record, no roller tracks, no rope fragments of the scale required, no tool marks consistent with the proposed conventional cutting method, no quarry waste pattern consistent with conventional extraction. What the standard academic response to this null result has been is classification. Proposals that fall outside the conventional mechanical framework are classified as fringe, and the classification substitutes for engagement with the evidence. This is a different thing from being wrong. Classification is institutional. Being wrong requires an argument. Grok was given the null result, no supporting evidence for any conventional model, and asked to approach the problem without a prior commitment to conventional mechanisms. To look at the physical evidence and identify what class of mechanism is actually consistent with what the site shows. The structural engineer on the team who reviewed the output spent 2 days looking for the error in the AI's reasoning before concluding that the error wasn't there. The team's instruction to Grok: analyze the physical characteristics of the Baalbek megaliths: weight, composition, surface finish, quarry geometry, transport path, placement precision, and identify what mechanism is consistent with all of the physical evidence simultaneously. The finding came back in 3 parts. The surface finish. The cut faces of the trilithon stones show a surface consistency that high-resolution photographic analysis of other megalithic sites does not show to the same degree. The pattern is more characteristic of vibration-assisted material removal than of direct percussion cutting. In modern manufacturing, vibration-assisted machining using acoustic or ultrasonic energy to reduce cutting resistance at the tool-material interface produces a specific surface microstructure distinct from struck surfaces. The trilithon surface microstructure is consistent with that category. This does not prove the mechanism. It means the surface is more consistent with vibration-assisted cutting than with the conventional tool marks the standard model predicts. The quarry geometry. The Baalbek limestone quarry is an enclosed space, a natural depression with steep limestone walls on 3 sides, modified by extraction activity. When Grok analyzed the quarry's dimensions against acoustic resonance principles, the same principles used in the design of concert halls and focused sound chambers, The quarry's enclosed geometry produces standing wave patterns at specific low audio frequencies, audible frequencies, frequencies in the range producible by human acoustic generation, voices, percussion, purpose-built resonant structures. The quarry is geometrically configured as an acoustic amplification chamber. Whatever sound is generated inside it at the right frequency, the limestone walls reflect, focus, and reinforce. The transport path. The 900 meters between the quarry and the temple site crosses limestone bedrock that shows no evidence of preparation for conventional sledge transport. If the effective weight of the stone, not its mass, but the force required to overcome friction and inertia, is reduced through acoustic pressure, the bedrock surface as it exists becomes adequate. The absence of road preparation is not a gap in the evidence for the conventional model. It is positive evidence for a model that does not require a prepared road. One mechanism is consistent with all three physical findings simultaneously: acoustic resonance at sufficient amplitude, generated within a quarry, geometrically configured to amplify it, applied to stones whose surface finish is consistent with vibration-assisted processing. As the team continued pulling the analysis, three additional findings emerged. The first revelation: the physics is not theoretical, it has been demonstrated. In 2015, researchers at the University of Bristol published results in the journal Nature demonstrating acoustic levitation and manipulation of objects at scales previously considered impossible. The mechanism creates standing pressure wave fields that generate net force on objects within them, reducing their effective weight relative to the support surface and enabling movement with dramatically reduced applied force. The 2015 work used ultrasound frequencies. The researchers explicitly noted in the paper that the scaling behavior of the phenomenon, whether the same principle could operate at lower frequencies with larger objects at sufficient amplitude, was an open question for further research. Grok cross-referenced the Bristol findings against the Baalbek quarry's resonance geometry, the quarry's natural amplification peak, the frequency the limestone walls reflect and reinforce most effectively, given the dimensional geometry of the enclosure, falls in the low audio range, not ultrasound, audible. The scaling question the Bristol team left open is exactly the question the Baalbek site geometry presents. The second revelation: the ancient texts that describe construction at Baalbek are not vague. The 11th century Sanskrit text Samarangana Sutradhara, a manual on architecture and engineering that explicitly draws on earlier source materials, contains passages describing sound as a functional component of stoneworking operations, not as ritual accompaniment. The text specifies that certain preparatory operations on stone were accompanied by specific sound production, and that the acoustic environment of the working space was a controlled variable. Modern scholarship has read these passages as describing ritual. The engineering reading, that the sound was mechanically active in the stone preparation, has not been published in a mainstream venue. The Arabic historical tradition recorded after the Islamic conquest of the Levant describes the people of Ad, a pre-Abrahamic civilization, as the builders of Baalbek. The physical description in these accounts, stripped of its cosmological framing, is specific. The stones moved as though lifted by the air, not dragged, not rolled, lifted by air. That is not a poetic description of organized labor. It is a physical description of a mechanism, one that matches acoustic pressure levitation more closely than it matches any conventional mechanical method. The third revelation: Göbekli Tepe in Turkey, the oldest known megalithic complex built approximately 11,600 years ago, presents a quarrying problem that predates Baalbek by thousands of years and shows the same pattern. Limestone T-pillars weighing up to 20 tons, quarried and erected at a site with no evidence of the ramp or lever infrastructure that conventional models require for objects of that weight. When Grok analyzed the Göbekli Tepe quarry geometry against the same acoustic resonance criteria applied to Baalbek, the result was the same: an enclosed quarry space with dimensional geometry that produces natural acoustic amplification at low audio frequencies. Same architectural signature. Different continent from Pumapunku in Bolivia, where the same pattern appears again. 3 megalithic sites, 3 continents, no documented connection between the cultures that built them, the same acoustic quarry architecture at each. The ancient textual record contains what may be the most consistent and most consistently ignored construction description in all of ancient literature. The first book of Kings describes the construction of Solomon's temple with a detail that mainstream biblical scholarship has never resolved. The stones arrived at the temple site already finished because no hammer or chisel or any iron tool was heard at the temple site while it was being built. Iron tools were used at the quarry. At the site, the stones were placed in silence. No striking, no dressing, no adjustment. They arrived and they fit. The Talmudic tradition explains this by reference to the shamir, a tool or substance that cuts stone without iron, without percussion, without the marks that iron tools leave. Modern scholarship treats this as legend. The physical description it produces, a cutting process that does not strike the stone and leaves it finished to a precision that requires no adjustment at the site, matches vibration-assisted processing more closely than any conventional alternative. In Egypt, the pyramid texts contain passages describing the movement of large stones using phrases that have been translated as metaphorical references to divine assistance. When read against the Samarangana Sutradhara passages and the Baalbek Arabic accounts, the same functional description appears across 3 languages and 3 traditions. Stone that moves without contact force, lifted or displaced by a medium that is not visible as a mechanism to observers who do not understand it. 3 textual traditions, 3 physical descriptions that match the same class of mechanism, all from cultures that built at scales that conventional models cannot fully account for. Here is what the academic response to the acoustic resonance hypothesis has not produced: a physical refutation. The hypothesis has been proposed in various forms for decades. The consistent institutional response has been classification, fringe, pseudoscience, outside the archaeological framework rather than engagement. Classification is not refutation. It is a decision about which proposals are worth testing, and the decision has consistently been not this one. The Bristol 2015 levitation paper was peer-reviewed physics. It was not fringe. It documented a real phenomenon at scales previously considered impossible. The researchers did not discuss ancient megaliths. The connection to ancient construction is an inference from demonstrated physics to a proposed historical application. Inferences require testing. The test is not complicated. Build an acoustic chamber with the resonance geometry of the Baalbek quarry, generate the predicted frequencies at the amplitude the quarry walls would produce, and measure the effect on a limestone block. The result would either support or rule out the mechanism as physically plausible at that scale. That test has not been run. The archaeologists who study Baalbek are not equipped to run it and have not requested it. The acoustic physicists who could run it do not study ancient construction and have not been asked. The question lives in the gap between 2 disciplines that do not communicate about this problem. The 650-ton stone of the south is still in the quarry, cut, finished, ready. It has been waiting since whoever placed the trilithon stones stopped work. Whatever stopped them, it was not the inability to move what they had already moved 3 times. So here's where this lands. The Baalbek trilithon cannot be explained by any conventional mechanical model that survives full physical analysis. Grok evaluated all of them. None pass. The surface finish of the stones is consistent with vibration-assisted processing. The quarry geometry is configured as an acoustic amplification chamber. The transport path shows no evidence of preparation for conventional sledge transport. The ancient texts from 3 independent traditions describe the same mechanism: stone moved by air without visible contact force. The same acoustic quarry architecture appears at Göbekli Tepe in Turkey and Pumapunku in Bolivia, in cultures with no documented connection to each other or to Baalbek. The structural engineer on the team described the output as the most unsettling result he had reviewed in 30 years of practice, not because it was wrong. he could not find the error. Because if it is right, the history of what human civilizations were capable of requires a revision that begins much earlier and reaches much further than the current textbooks allow. When the team asked Grok to model the specific frequency that would produce sufficient acoustic pressure to allow movement of a 1,000-ton limestone block with a realistic ancient labor force generating and focusing sound within the quarry's geometry, the output was a specific number, one frequency. And when that number was cross-referenced against the dimensional resonance analysis of the Baalbek quarry, the frequency the enclosed limestone walls amplify most strongly given the measured dimensions of the space, they matched. Not approximately, not within the same range. The frequency the model requires and the frequency the quarry amplifies are the same number. The quarry was not selected for the quality of its limestone. There is better limestone closer to the temple site. The quarry was selected because its geometry, the specific shape and dimensions of the enclosed space, produces exactly the acoustic conditions that the movement method required. Someone designed the quarry not to extract stone, to move it. The 1,650-ton stone is still there. The quarry still has those walls. The physics still works the same way it worked when whoever built the trilithon was working in that space. We know the frequency, we know the geometry. What we don't know yet is who taught the first person which note to use. Subscribe now and turn on notifications. When the next piece goes up, you need to have seen this one first. I'm Dr. James Mercer. The moment I have more, you'll be the first to know.